Greetings and welcome, ladies and gentlemen of the internet. We're talking about modeling motion with matrices today. We're going to still use some of our previously learned skills, such as adding, subtracting, and multiplying matrices in order to do this. The first thing we're going to talk about is the fact that you can use a matrix to represent the vertices of some two-dimensional figure. Technically, you could even represent a three-dimensional figure with it as well. So let's say, let's draw a little sketch here. And let's say bum, 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 bum. Let's see, just go 4 in every direction. That'll be fine. 3, 4. 1, 2, 3, 4. And let me plot like a little guy. So let's say I've got, let's make it super simple. Let's go plot 1 point at the origin. That'll be point A, right? We'll plot 1.3 units to the right. So that's 3, 0. That'll be point B. And let's plot 1 point 0, comma 4. And that'll be point C. So I've got like a little representation of a triangle. And this is actually, using matrices like this is how many computer graphics are going to be accomplished as well. Even in 3D, I could have kind of a three-dimensional polygon going on here, you know, like Pixar or whatever, and they would represent the location of all of their, you know, vertices with some sort of math, right? So let's say I've got this vertex matrix, and this is what I'm going to do. I'm going to have my vertex matrix set up, and you can actually have any number of vertices represented in this. It's always going to be 2 rows, where you wouldn't label this normally, but the top row or the first row is x coordinate and the second row is y coordinate. And then all of the remaining rows are going to be your points, okay? Is the idea. All right, this one's going to be a 2 by 3 because I have 3 points to represent. All right, so I'm going to have kind of point, you know, A here, B, and C. And you don't, like I said, you don't normally label the, you know, the outside of the matrix. I'm just indicating to you why I'm filling out the information as I am. So let's see, point A. What are the coordinates of point A? 0, 0, right? So I'm going to represent it that way, right there. What are the coordinates of point B? 3, 0, right? X first. And then point C is 0, 4. All right, so this is called a vertex matrix, and it's just simply representing all of those points, all of those locations, right? And now what I'm going to be able to do to this vertex matrix is either add stuff to it or multiply it by stuff, and that will give me multiple transformations to my original figure, which we'll call the pre-image is the original figure, and the image will be the new kind of result of those changes. So let's do, so types of transformations we can do. You've seen all of these before. Transformations, you can do translations, which is like a shift, right? So shift it up 1 unit and left 2 units or something like that. We'll be able to do reflections, where I can reflect it over a particular axis or something like that. And we can even do rotations. And I think actually there might even be a way to do what's called a dilation. Does anyone know what a dilation is? A dilation is essentially scaling it up. Yeah, I think one of our students had a hand gesture there that was accurate. They were kind of like squishing their hands together or spreading their hands apart. So it's scaling up by some factor. And actually, even the word scale is going to help us understand that. I could actually multiply this by a scalar. Scalar. For instance, if I multiply this matrix all by 2, I would end up getting a dilation that doubles the at least linear size of the figure. I believe it would quadruple the area of the figure, but nonetheless, those are the types of transformations we can do. So let's say I want to do a translation. Translate triangle ABC up, or no, actually we'll do down. How about down 2, and left 1. Okay? So I've got my little vertex matrix, my starting point, 0, 3, 0, 0, 0, 4, right? And in order to translate this, what would shifting down 2 do to my coordinates, every one of them? I want to, what, subtract 2 from which coordinate? The y-coordinate, right? Down is in the vertical direction, right? So what I'm going to do is I'm going to add a matrix where I'm going to add a -2 to all of the y-coordinates. What's the size of this matrix going to have to be? It's going to have to be the same size as that. So this one's going to have to be a 2 by 3, right? So my bottom row is going to be all -2s, and I'm going to have 3 of them. Okay? And what do I have to do to my x-coordinates? Yeah, subtract 1, so I'm going to put -1s in all of these locations. And if I add these two together, I'm going to get a new vertex matrix of my image. All right? So this is actually going to be, I guess I could call it triangle A prime, B prime, C prime, right? So how do you add matrices? What do you do? Yeah, the same one. Okay. The way we would say that is you add corresponding elements together in order to get those. So 0 and -1 is -1. 3 and -1 is 2. 0 and -1 is 2. 0 and -2. What? Oh, what? Classic. You guys caught me, though. You got my back. I appreciate it. 0, -2 is -2. 0, -2 is another -2. And 4, -2 is +2. So this is my new matrix, right? And I just want to point out that horizontally, my first row is the x, my second row is the y. What's my first column represent? A prime, B prime, and C prime. So I could actually represent this, I could translate this back out. I guess translate's probably a bad word. In this case, it's redundant. I could rewrite this as points if I wanted, where I could say A prime is the point -1, -2, B prime is the point 2, -2, and C prime is the point -1, 2. All right, so if you wanted to work with ordered pairs, I could take it out of that vertex form as well if I wanted. So let's actually graph where this is. So let's see, A prime, I'm going to scroll back up to my little picture, is -1, -2. So left 1, down 2. Right there's A prime for us, right? Bam. B prime is 2, -2. So over 2, down 2. Right there is B prime. And C prime is -1, 2. So I'm going to go left 1, up 2. And if I draw my image, you can see that the purple triangle here is in fact shifted, left 1, down 2 for all of their points. Not just the vertices, but even if I considered any of the points, the infinitely many of them along the edges of that polygon, it also shifted those by the same amount, which is cool. So translation, perhaps not that impressive, right? I don't know. Perhaps not. I don't know. Are you guys impressed by that? It's just like adding numbers. But if I wanted to, teach a computer to do this, this is kind of what I would do, where I'd have my graphics or whatever, and kind of behaves on a base level. I mean, chances are, game designers and stuff would use us, or Pixar movie creators would have an engine that already does a lot of this in the background, so they're not doing this. But the computer had to be programmed at some point to understand it to that level. And if I wanted to animate, I could even have some variable t component to all of these, where over time, right, it's shifting by that amount, and then it would actually have kind of like a translation over time, and you'd actually see the triangle moving on the screen in that direction over time, and I could use what we'll later call vectors and stuff to do that. So that's translation. So that's kind of a little bit interesting. Let's talk about reflection. All right. Let's talk about reflection. Let's see. Let me draw a new picture. I'm going to go out maybe the same size as last time. Let's see. 1, 2, 3, 4. I actually only have to go, I think, 2 high and 2 low and just 1 back. There we go. So I'm looking at that. And let's see if we can figure out a way to do this reflection. All right. So this is what we got. Actually, this might end up having us solve a system. We'll do this. I might just give you the formulas rather than derive some of them in this case. But let's say I've got a triangle here. Another triangle, because we're fans of triangles. Why not? So here's point A. Here's point B. And let's have point C be, I don't know, 3, -2. All right, so here's our triangle. No guarantee that that's the actual x-intercept there, down 2 over 1 down. Actually, it is. But. So here's our triangle. Could you give me a vertex matrix that represents this triangle? Well, actually, first of all, what would the size of this vertex matrix be? It'd be 2 by 3. All right, vertex matrices, at least in 2 dimensions, are always going to have 2 rows. If I wanted 3-dimensional points, I could have 3 rows, and then any number of columns. So let's see, and yeah, 2 by 3. So what's my vertex matrix going to be? For point A, -1, 0. Point B is 1, 2. 3, -2. Right? So there's our vertex matrix. And I'm going to cheat just a little bit, just to save us some time. These formulas, or these little reflection matrices, are in your book. This is on page 90, if you're wondering. I'm going to paste this right here. Blam! Your book. So this is on page 90 of the advanced math textbook. Right. So, and on the quiz, by the way, I'll give these to you because I don't feel like having you memorize a whole bunch of zeros and ones. That's kind of craziness. But all right, so this is the idea, is if I want a reflection over the x-axis, this little matrix is referred to as r sub x axis or whatever, I can actually multiply my matrix by this guy right here. So let's see if I can reflect this over the x-axis. So this is the x-axis here, right? And actually, let's do this by hand first, and then we'll use matrix multiplication to figure it out. If I reflected A over the x-axis, where would A prime go? Same place, right? It's reflected onto itself. If I reflect B over the x-axis, where would B go? It'd be down here, right? So this would be B prime. Actually, let me get rid of that line just so it doesn't clutter our image, right? So B prime. Oh, A prime. I didn't label that prime. And if I reflected C, where would C be? It'd be over 3 up 2, right? Because it has to be the same distance from the x-axis perpendicular to it for the mirroring to work. And I would have my little shape like this, right? Bam, bam, bam. So what does my image vertex matrix look like? Let's see, A was in the same spot, so that's -1, 0. B is now over 1 down 2, right? And C is over 3 up 2. How do these two matrices relate? What's the similarities between these guys to reflect over the x-axis? What's the same? Which ones are switched? All of them? The y's are switched, right? The whole x row is all the same. right? And the y row has been changed in sign, which makes sense, right? I mean, if I change this y-intercept, it flips it up there. If I change that y-intercept, it flips it down there. And it all kind of works out. So I'm going to look for a matrix that I could multiply this by that's going to just change the sign of the y-coordinate. And they're claiming this is that matrix. Let's see. So they're saying you multiply your vertex matrix by this. All right, if I'm to do that, what side do I multiply it on, and or does it matter? If I want to multiply my green matrix here by this, what side which is multiplied by which? Which is left and which is right?
Wouldn't that 2 by 2 would be right or left in the first one?
Why do you say that?
Because it has to match up with the 2 on the other side. That's 2 by 3.
Right. So I can't multiply a 2 by 3 by a 2 by 2, correct? Because the inner numbers wouldn't match. But I can multiply a 2 by 2 by a 2 by 3 because the inner numbers would match in that case. So it turns out these reflection matrices always have to be on the left side to do the multiplication. So well done. Good analytics there. So we've got 1, 0, 0, negative 1. I'm going to multiply that by my vertex matrix of negative 1, 0, 1, 2, 3, negative 2. And let's multiply this out and see if we get our expected answer here. All right. I'm going to zoom through some of this. So what is the size of my answer matrix going to be? So it's 2 by 2, 2 by 3. So my answer is going to be a 2 by 3 matrix, right? Which I would hope my triangle, when reflected, will still have 3 points in the end. So hopefully it's the same size. So this does seem to match up, right? Okay. Now, so let's multiply this out. So roll call. Here we go. 2 by 3. 1 times negative 1 is negative 1. 0 times 0 is 0. Right? 1 times 1 is 1. 0 times 2 is 0. 1 times 3 is 3. And 0 times negative 2 is 0. So do you guys agree that my first row has no change taking place to those x coordinates, right? Because it's really multiplying by this 1, 0 row is just giving me exactly the same numbers, right? Because I'm just adding 0 to all those. All right. Now let's get the second row calculated. So 0 times negative 1 is 0, plus negative 1 times 0 is 0. Okay, so that one's not that interesting. Let's see, second row, second column. Multiply the second row by the second column. So 0 times negative 1 is 0. Sorry, I have lied. 0 times 1 is 0, plus negative 1 times 2, right, that's going to be negative 2. And second row, third column, 0 times 3 is 0, plus negative 1 times negative 2 is positive 2. I guess I don't need parentheses there. And so behold, what do I get? Well, actually, let's analyze the second row first. Notice that these zeros did nothing, right? So that's what this kind of 0 had to do with the play. And the negative 1 opposited all of these guys, right? Which is what I wanted. I wanted to opposite, change the sign, whatever, of my y coordinates. So I'll have negative 1, 1, 3, and 0, negative 2, 2. And that does appear to line up. Bam, bam. All right. So it turns out, depending on what I'm going for, reflection over the x-axis, y-axis, or over the line y equals x, what does the line y equals x look like? Line y equals x. It's the diagonal with a positive slope, 45 degrees. That's y equals x. Right? So it would reflect over that line right there. So some of these, I mean, once you do one problem with it, you can see, okay, oh yeah, that matrix does do exactly what I'd want it to. It's not that bad. Let's consider one more type of transformation. Looks like I'm out of room at the bottom of this page, so I'm going to scroll over right here. And let's take another snapshot. Tell you what, bam, again, page 91. Man, I love how quickly I can do this. Bam. There it is. These are rotation matrices. These matrices are specifically regarding counterclockwise rotation. You might wonder why that's the natural rotation path that mathematicians prefer. I'll talk about that a little bit later on in Math 4 when we're doing some trigonometry. But that is counterclockwise is the natural rotation for the way we measure angles. So let's do an example again. Tell you what, let's use the same vertex matrix. What was our original matrix? It was 0, 0. No, I lied. Not our original one. What was the one we just did? We had 1 point at negative 1, 0, was it?
Negative 1, 0.
Oh, then over 1 up 2, and then over 2 or over 3 down 2. Okay. So there's the same matrix. This time, let's rotate. I don't know, let's do 90 degrees. Okay? So what am I going to do? I'm going to steal this little matrix right here. And let's see, Christiana, can you figure out what side I'm going to multiply this matrix on? Still has to be on the left side every time. Even if I was rotating a square or a pentagon or some, crazy 30-sided polygon that I had drawn out, as long as I knew all of the vertices, I'd have a 2 by 30 matrix representing the vertices, and I'd multiply this on the left-hand side exactly. So let's do that. So let's multiply. I think I left myself enough room-ish. It's going to look a little sloppy, but hey, what the heck. So 0, negative 1, and 1, 0. So rotating 90 degrees. I'll have to consider what that's going to look like. So let's do this out here. So row by column. I can multiply these first of all because the inner numbers for the sizes match, 2 by 2 and a 2 by 3. I'm expecting a 2 by 3 answer. So let's see, I'll have 0 plus 0 because 0 times negative 1 is 0 and negative 1 times 0 is 0. Next one, 0 times 1 is 0 and negative 1 times 2 is negative 2. 0 times 3 is 0 and negative 1 times negative 2 is positive 2. Oh, look how embarrassing that is right there. Closing a matrix with a parenthesis. Please. Let's see. Next row. 1 times negative 1 is negative 1 plus 0. Some interesting stuff going on here. 1 times 1 is 1 plus 0 times 2 is 0. And let's see. 1 times 3 is 3 plus 0. Okay. So let's write this out. So we'll have 0, negative 2, positive 2, negative 1, 1, 3. So this is my image. This would be my points A prime, B prime, and C prime. Can you tell me what's going on here? It looks like I switched the X's and the Y's. And which signs changed? All right, the top row became the second row, right? So my X's became Y's, and my Y's became X's, but I changed the sign of those ones, right? Okay, so there's some stuff going on there that is interesting. You could actually do some kind of analytics on the coordinate plane to figure out how it all works out. But let's draw this. 0, negative 1. Let's see, I'm going to draw it on my old coordinate. You guys, you got those points written down, so I'm going to ask you for them in a moment. Let's see, I'm going back to my old graph here. Here it is. I actually will probably need some more points over here. If you don't have room to draw it on yours, that's fine. Don't worry about it. You'll at least see it here. So what was my first point? It was what, 0, negative 1? So 0, negative 1 is down here, right? What's B prime? So negative 2 up 1. Okay. And what's my next one? C prime? Over 2 up 3. Up 3. Okay, so I have to do that. So this is probably not the clearest image because I've got 3 graphs on top of the same thing. But let's see. What was this supposed to do? rotate 90 degrees. So let's see, from A to my new A prime, that's 90 degrees clockwise. Let's see, here's B. What's this angle here that I just drew? Looks like 90 degrees, and it's clockwise. What? And for point C, look at this angle right here. How cool is this? Bam, bam, is 90 degrees. And what? I realized that picture right there, if someone just walked in here and looked at that, they're like, what? That doesn't help anything. But I just want to point out that that's what we got. It worked out. It did what we intended. So you can actually accomplish some interesting translations, rotations, and such using these matrices, which is good stuff. Good stuff. And then I guess I'll mention the concept of a dilation. By a factor of 3, let's say. All I would do in this case is I'd multiply whatever my vertex matrix is by 3. I'm not even going to do this one out, I don't think. Right? Well, what the heck, I've got time. Negative 1, 0, 1, 2, and then what was it, 3, negative 2? Did I get it right? Bam, bam. So let's see, dilation, or multiplying by a scalar is really easy. It's essentially just distributive property where I'm just multiplying this. Yeah, to multiply by a scalar. So that's kind of nice and easy. So this one's going to equal negative 3, 3, 9, and 0, 6, negative 6. And if I was to plot those points, you'd realize that your triangle is 3 times as large, linearly speaking. It would actually be 9 times as large in terms of area, if you wanted to think about it that way. So I could fit 9 of the old triangle into my new triangle. But the edges are only 3 times longer. Okay. So that's the idea of a dilation. All right. Actually, I'll even show you a quick little picture of, there's a dilation of a half factor, is that? Yeah, 0.5. So you can see that the blue cut down half in size linearly, and now that kind of works out. So there's an example of a graph of a dilation. So I think we're good. All right, internet friends, thanks for watching. Bye.